Hello, welcome back. I'm excited for today's lesson because I love related rates. They're so cool. Now, to be fair and to be honest up front, they can get a little bit complicated, but if you stay organized, it's just really cool how this all works together. Two questions for today. How fast are variables moving with respect to time? And can you account for several variables at once? In general, time rates of change answer the question, how fast is a quantity changing? For example, if V is volume that is changing in time, then dV dt is the rate the volume is changing with respect to time. If a person is walking towards a bus at a constant rate of 3 feet per second, then we know the distance is decreasing. So dW dt would be negative 3 feet per second. If they walk away from the bus, then the distance is increasing and the rate of change becomes positive, or dW dt equals 3 feet per second. We're going to start our adventure in related rates by doing a bit of translating and some simple implicit differentiation to get you warmed up. Translate the following from English to calculus. The volume of a cylinder is increasing at a rate of 6 cubic feet per second. That would be dV dt equals 6 feet cubed per second. Number 2, the depth of water in the new Pine Creek High School pool is decreasing at a rate of 2 inches per hour. Decreasing. So the HDT, sometimes we use height for depth because dt just gets complicated. Anyway, the HDT equals negative 2 inches per hour. The number of vehicles driving on the C470 toll road is increasing at a rate of 85 vehicles per hour. That could be dV dt, maybe V would be vehicles, equals 85 vehicles per hour. Air is escaping from a happy birthday balloon at a rate of 15 cubic centimeters per second. So we could say dV dt, V being volume, is negative 15 cubic centimeters per second. Now we're going to do some quick implicit differentiation with some equations or some formulas that hopefully you've seen before. So the area of a rectangle, we're going to differentiate this with respect to time. So we take the derivative of both sides with respect to time, and notice on the left we have two functions being multiplied together. So we're going to use the product rule. dA dt equals, the derivative of the first, the derivative of L with respect to time is dL dt. Derivative of the first times the second plus derivative of the second, dW dt, times the first. So any variable that we take a derivative of that's not t is going to get this dt added onto it. Number 6, the circumference of a circle is 2 pi r. So we've got a constant and a variable. So dc dt equals 2 pi dr dt. Volume of a cube, we got the 3 that comes forward. dV dt equals 3s squared ds dt. I'm going to go a little bit faster now. Area of a circle, dA dt equals 2 pi r dr dt. Perimeter of a square, dP dt equals 4 ds dt. When I'm saying it out loud, it sounds like, I don't know, alphabet soup. Volume of a cylinder, we've got two functions again, so product rule. Oh wow, dV dt equals 2 pi rh dr dt plus pi r squared dh dt. Now this isn't exactly the order of derivative of the first times the second plus derivative of the second times the first, But I kind of rearranged it so that dRdt and dHdt were on the end, just to make it prettier. Volume of a cone. Oh, we've got product rule again. dV dt equals 2/3 pi r h dr dt plus 1/3 pi r squared dh dt. Whew. And side lengths of a triangle. This is an important one, actually. So that would be 2x dx dt plus 2y dy dt equals 0. Here we go with example 1. Suppose x and y are differentiable functions of t and are related by the equation y equals x squared minus 3x. Find dy dt when x equals 3, given that dx equals 2 when x equals 3. There is so much information in that, so we're going to read it again and write down the information as we read it. Suppose x and y are differentiable functions of t and are related by the equation y equals x squared minus 3x. Find dy dt, that's what we're looking for, when x equals 3, given that dx dt equals 2. So writing all this stuff down, everything you know, what you need to find, is a really important first step. Now we'll take the derivative of our equation. dy dt equals 2x dx dt minus 3 dx dt. And now it's just a matter of plugging in the information that we've written down up here. So dy dt equals 2 times 3, that's x, times 2 minus 3 times 2. So plug in dx dt and x, and then simplify it. So dy dt equals 6. Example 2. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 feet per second. When the radius is 4 feet, at what rate is the total area, A, of the disturbed water changing? Okay, so we just read it. We got an overview. Now we're going to read it again, writing stuff down as we go. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Draw a picture if you can. The radius r of the outer ripple is increasing at a constant rate of 1 feet per second. So dr dt equals 1 foot per second. When the radius is 4 feet, r equals 4, at what rate is the total area of the disturbed water changing? We're looking for a rate of area, so that's dA dt. Well, the area of what? Oh, the area of a circle. Area equals pi r squared. So we have all the information we know, and we can start working the problem. So we'll take the derivative of both sides with respect to time. dA dt equals 2 pi r dr dt, and then plug in what we know. So dA dt equals 8 pi. But what is 8 pi? That's a rate of change of area. We're talking about feet, okay? And we're talking about seconds. So the label to this would be feet squared per second. So here's your step-by-step guide on how to attack a related rates problem. Step 1, read the problem. Step 2, reread the problem, and as you do, make a sketch, write down what you know and what you're looking for. Write an equation. Then differentiate both sides with respect to time, substitute known values, and solve. Let's try another one. The volume of a sphere is 4/3 pi r cubed. Air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute, How fast is the radius of the balloon changing at the instant the radius is 30 centimeters? Okay, so we read the problem. Now we're going to read it again and write down what we know as we go. The volume of a sphere is 4/3 pi r cubed. Air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. So that's dV/dt. That's the rate of the volume is 800 cubic centimeters per minute. How fast is the radius of the balloon changing? We're looking for the RDT at the instant that the radius is 30 centimeters. Once we have all of our information written down, let's solve it. So take the derivative of both sides with respect to time. dV/dt equals 4 pi r squared dr dt. Plug in what we know. 800 equals 4 pi 30 squared dr dt. And now we just need to isolate dr dt. So we'll divide both sides by 40 pi 30 squared. And actually, you can leave it right like that. You don't have to simplify those numbers unless you want to. And I don't want to right now. So I'm going to stop there. And the only thing left is to add a label. So we're doing the rate of the radius. That's one dimension. So that's just centimeters per minute. Example 4. The top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? Okay. So the top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute, which means at the same time, its bottom is getting away from the wall. So dy dt is negative 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? So we're looking for dx dt. We don't have an equation to use at this point, but we do have a right triangle with sides y and x and a hypotenuse of 25. So we actually do have an equation we can use, the Pythagorean theorem. X squared plus y squared equals 25 squared. Take the derivative of both sides, and then we'll plug in what we know. We're looking for dx dt. We know y, we know dy dt. And now we can start to isolate dx dt. 2x dx dt equals 42, and we'll divide both sides by 2x, and then we have a problem. X. What the heck is x? Is there a way that we can solve for x? Well, let's go back to our triangle, and I can erase the y there, and I can make that a 7. All right. X squared plus 7 squared equals 25 squared. So x equals 24. Now I can plug that in. I'll simplify this. dx dt equals 7/8. What's my rate? So we're dealing with feet and minutes. So feet per minute. Example 5. At noon, ship A is 150 kilometers east of ship B. Ship A is sailing west at 35 kilometers an hour, and ship B is sailing north at 25 kilometers an hour. How fast is the distance between the ships changing at 4 p.m.? Okay. I'm just going to apologize for this one in advance. There's a lot going on in this one, and it gets complicated. But again, it's so cool. And don't worry if you think to yourself, okay, I would never have thought to do that, because you're in the learning mode. I'm teaching you. So here we go. At noon, we have ship A, and he is 150 kilometers east of ship B. Ship A is sailing west at 35 kilometers an hour. Notice what I did here. I've got 150 minus x because you're starting at 150 and decreasing by x as the guy moves west. Ship B is sailing north at 25 kilometers an hour. How fast is the distance between the ships changing at 4 p.m.? Okay, well, the distance is going to be the hypotenuse between the two ships at any given moment. And we're looking for dz dt, or the rate of change of that distance. Once again, we have a triangle, but we can't use x squared right there. We have to use the 150 minus x, because that's actually the length of the side of that triangle. We have all the information, so let's start solving, taking the derivative with respect to time, and dx dt, dy dt, and dz dt. Each of these we have accounted for up here. However, we don't know x, y, and z. Can we figure those out? Yes, we can. And the key to that is this 4 p.m. So the ships started sailing at noon, and now it's 4 p.m. So we know how long they've been sailing and at what rates they've been sailing. So at 4 p.m., when t equals 4, x has become 4 hours times 35 kilometers an hour, so that's 140. Y is 4 hours times 25 kilometers an hour, so that's 100. And then z looks terrible, but you can use Pythagorean theorem, and I'll just tell you it's 10 times the square root of 101. Now let's regroup and see if we have all the information we need. Before we start plugging stuff in though, let's get rid of those 2's. Now we can plug in our x, dx dt, y, dy dt, and z and dz dt. Then we just simplify from there. You can trust my algebra if you want, or you can verify it on your own. dz dt at y equals 4 hours is 215 over the square root of 101. We need a label. So dz dt, that's going to be kilometers per hour. Okay, we're going to go back to a more straightforward question, and then we're going to end with another bonus doozy question. Example 6, a right circular cylinder is changing shape. The radius is decreasing at a rate of 2 inches per second, while its height is increasing at a rate of 5 inches per second. When the radius is 4 inches and the height is 6 inches, how fast is the volume changing? And there's a formula. So that's our overview. We're going to read it again and write down the information as we go. A right circular cylinder is changing shape. The radius is decreasing at a rate of 2 inches per second, while its height is increasing at a rate of 5 inches per second. When the radius is 4 inches and the height is 6 inches, how fast is the volume changing? We have all our information. We know that the volume is pi r squared h. Now we start solving. Taking the derivative with respect to time of both sides, we get dv dt equals 2 pi r h dr dt plus pi r squared dh dt. And let's see, r we have accounted for, h we have accounted for, dr dt, r dh dt. Ha! All of that information is accounted for up here, so we just have to plug it in. That simplifies to about negative 96 pi plus 80 pi. So that's negative 16 pi. We need a label. If this is the volume decreasing, then that's going to be inches cubed per second. Last one, and please take a deep breath before we start this one. We have an inverted cone that's leaking water at a rate of 1 cubic centimeter per minute. The cone has a height of 9 and a radius of 3. Find the rate at which the water level is dropping when h equals 3. And there we have our formula. So, inverted cone. It's leaking water at a rate of cubic centimeters per minute. So that's volume. dV dt is -1. The cone has a height of 9 and a radius of 3. Find the rate at which the water level is dropping, so that would be dH dt, when the height is 3, given 1/3 pi r squared h. Whoa, wait a second. Why do we have two heights? Well, we want dV dt when the height is 3. So that's the h we'll use, but then is there an r that goes with it? Okay, put your pencil down. Literally stop taking notes for a second. Just watch, because I need to show you something. I'm going to go ahead and start solving this problem. So I'll take the derivative of both sides with respect to time, and then plug in the information we know. We've got h accounted for, we have dH dt accounted for, but we don't have r or dr dt. So like we've done before, we can actually solve for r. If you remember back to geometry and similar figures, we can use similar triangles to solve for r. So if the big triangle up here is the radius of 3 and a height of 9, well, as it shrinks, I'll have a radius of, I don't know, with a height of 3. So I can set up a proportion and solve for r, and r equals 1. Got that one, but what about dr dt? There's no way to manufacture or calculate dr dt, so we're stuck. R is a problem. So you know what? We need to get rid of r. We're going to go back to, and you can start taking notes again now, let's go back to our similar triangles. This is when this h equals 9 and r equals 3 comes in handy. So 3 and 9. Now, as the height shrinks, so does the radius. As h is decreasing, so is r. And if we leave r and h as variables, we can cross multiply and solve for r. And actually, r is always 1/3 of the height. So let's go back to our formula here, and instead of writing an r, we're going to write that h over 3. Clean it up, and look at our new equation. There's no r. So now let's see what happens. We'll take the derivative with respect to time of both sides, and when we do, we have dV dt, we have h, and we're looking for dH dt. So we'll plug in what we know. That 1/9 and the 3 squared, those are going to kind of cancel each other out. We can isolate dH dt to be -1 over pi. We did it! We just need a label. So this is the height, that's 1 dimension, so we'll have centimeters per minute. Wowza, right? There was so much in that. And I know probably these similar triangles seem to come out of nowhere, but you'll get used to it. Practice makes perfect. And just remember, if you start going through the problem and you realize that you just can't get all the information you need, see if you can eliminate a variable and try again. Thank you for being here. Good luck with your practice.